Now that we've looked at evaluation of binary classifiers, let's take a look at how the more general case of multi-class classification is handled in evaluation. So, in many respects, multi-class evaluation is a straightforward extension of the methods we use in binary evaluation. Instead of two classes, we have multiple classes, so the results for a multi-class evaluation amount to a collection of true versus predicted binary outcomes per class. And just as we saw in the binary case, you can generate confusion matrices in the multi-class case. They're especially useful when you have multiple classes because there are many different kinds of errors that result from one true class being predicted as a different class. So we'll look at an example of that. Classification reports that we saw in the binary case are easy to generate for the multi-class case. Now, the one area which is worth a little more examination is how averaging across classes takes place. There are different ways to average multi-class results that we'll cover shortly. The support, the number of instances for each class, is important to consider. So just as we were interested in how to handle imbalanced classes in the binary case, it's important, as you will see, to consider a similar issue of how the support for classes might vary to a large or small extent across multiple classes. There is a case of multi-label classification in which each instance could have multiple labels. For example, a web page might be labeled with different topics that come from a predefined set of areas of interest. We won't cover multi-label classification in this lecture. Instead, we'll focus exclusively on multi-class evaluation. The multi-class confusion matrix is a straightforward extension of the binary classifier 2x2 confusion matrix. For example, in our digits dataset, there are 10 classes for the digits 0 through 9. So the 10-class confusion matrix is a 10 by 10 matrix with the true digit class indexed by row and the predicted digit class indexed by column. As with the 2x2 case, the correct predictions by the classifier, where the true class matches the predicted class, are all along the diagonal, and misclassifications are off the diagonal. In this example, which was created using the following notebook code, based on a support vector classifier with linear kernel, we can see that most of the predictions are correct, with only a few misclassifications here and there. The most frequent type of mistake here was apparently misclassifying the true digit 8 as a predicted digit 1, which happened 3 times. And indeed, the overall accuracy is high, about 97%, as shown here. As an aside, it's sometimes useful to display a confusion matrix as a heat map in order to highlight the relative frequencies of different types of errors. So I've included the code to generate that here. For comparison, I've also included a second confusion matrix on the same dataset for another support vector classifier that does much worse in a distinctive way. The only change is to use an RBF radial basis function kernel instead of a linear kernel. While we can see from the accuracy number of about 49% below the confusion matrix that the classifier is doing much worse than with the linear kernel, that single number doesn't give much insight into why. Looking at the confusion matrix, however, reveals that for every true digit class, a significant fraction of outcomes are to predict the digit 4. That's rather surprising. For example, of the 44 instances of the true digit 2 in row 2, 17 are classified correctly, but 27 are classified as the digit 4. Clearly something is broken with this model, and I picked this second example just to show an extreme example of what you might see when things go quite wrong. This digits dataset is well established and free of problems, but especially when developing with a new dataset, seeing patterns like this in a confusion matrix could give you valuable clues about possible problems, say in the feature preprocessing, for example. So as a general rule of thumb, as part of model evaluation, I suggest always looking at the confusion matrix for your classifier to get some insight into what kinds of errors it is making for each class, including whether some classes are much more prone to certain kinds of errors than others. Next, just as in the binary case, you can get a classification report that summarizes multiple evaluation metrics for a multi-class classifier, with an average metric computed for each class. Now, what I'm about to describe also applies to the binary class case, but it's easier to see when looking at a multi-class classification problem with several classes. So here's an example of how to compute macro average precision and micro average precision on a sample data set that I've extracted from our fruit data set. In this example, we have 3 columns, where the first column is the true class of an example, the second column is the predicted class from some classifier, and the third column is a binary variable that denotes whether the predicted class matches the true class. And here we have this is a multi-class classification problem. And so we have 3 classes here. We have several instances that are of the orange class. We have 2 instances that are the lemon class, and we have 2 instances that are the apple class. So in this first example, we'll compute macro average precision. And the key aspect of macro average precision is that each class has equal weight. So in this case, each of these classes will contribute 1/3 weight towards the final macro average precision value. So there are 2 steps to compute macro average precision. The first one is to compute the metric. So in this case, we're going to compute precision within each class. So let's take a look at the orange class. There are 5 total examples in the orange class, and only one of them was predicted correctly by the classifier. And so that leads to a precision for the orange class of 1 out of 5, or 0.20. For the second class, the lemon class, there are a total of 2 instances, and only one of them was predicted correctly, and that leads to a precision of 1/2, or 0.50, for the lemon class. That's right, the precision for each of the classes that we have calculated. So this was and for the third class, the apple class, the classifier predicted both of these correctly, so that's a precision of 2 out of 2, or 1.0. So that's the first step. We've computed the precision metric within each class. And then in the second step, we simply average these across these 3 to produce the final result, to get our final macro average precision. And so we can simply compute the average of 0.2, 0.5, and 1, and we get a final macro average precision for this set of results of 0.57. You'll notice here that no matter how many instances there were in each class, because we computed precision within each class first, each class contributes equally to the overall macro average. So we could have had, for example, 1,000,000 examples from the orange class, but that class would have still been weighted equally because we would have first computed precision for the 1,000,000 orange examples, and then that number would still get 1/3 of the weight compared to the other 2 classes. So that's macro average precision. Micro average precision is computed a little differently, and it gives each instance in the data results here equal weight. In micro average precision, we don't compute precision for each class separately. We treat the entire data set the entire set of results here as an aggregate outcome. So to compute microaverage precision, we simply look at how many of all of the examples. We have 9 examples here in total. And microaverage precision will simply compute the precision for all the examples regardless of class in this set of results. So out of these 9 instances, we have found that the classifier predicted 4 of them correctly. And so the microaverage precision is simply computed as 4 divided by 9, or 0.44. And you'll notice here that if we had 1 million instances of the orange class, for example, that with microaverage precision, because each instance has equal weight, that would lead to the orange class contributing many, many more instances to our overall microaverage precision. And so the effect of microaverage precision is to give classes with a lot more instances much more influence. So the average here would have been influenced much more by the million orange examples than by the 2 lemon and apple examples. And so that is the difference between micro and macro average precision. If the classes have about the same number of instances, macro and micro average will be about the same. If some classes are much larger, have more instances than others, and you want to weight your metric toward the largest ones, use micro averaging. If you want to weight your metric towards the smallest classes, use macro averaging. If the micro average is much lower than the macro average, then examine the larger classes for poor metric performance. If the macro average is much lower than the micro average, then you should examine the smaller classes to see why they have poor metric performance. Here we use the average parameter on the scoring function. In the first example, we use the precision metric and specify whether we want micro average precision, which is the first case, or macro average precision in the second case. In the second example, we use the F1 metric and compute micro and macro averaged F1. Now that we've seen how to compute these metrics, let's take a look at how to use them to do model selection.